Hello, everybody. It's just turned 12 o'clock, so we'll make a start. I would like to welcome you all to our final Train Talks at 12 webinar. So in this final session, we will be looking at how to measure the effectiveness of your friction management program and give you some insights into our personal experience of running trials, evaluating friction management regimes. For those of you who this is the first webinar that you've tuned into, I'm Jackie Butterfield. I'm the lead applications engineer for LB Foster in Europe. So I'll run through the slides, and then at the end there will be an opportunity for question and answer, not just on trials and validation, but if you have any questions at all on the previous webinars, I would be happy to take your questions. So in this final webinar, I just want to start by just taking a very brief look at what we've discussed in the past 7 webinars in terms of the issues that can arise from uncontrolled friction in the wheel rail interface and what friction management solutions are available and effective. And then I'll look at the reasons why we need to or want to undergo trials and validation exercises, and what are the key factors that we need to consider in order to deliver a successful trial. I'll briefly go through a few examples of different types of trials and tests and specific considerations that are required for these types of trial. And then finally, I'll list just a few useful resources that you can look at to help with trialing, planning and executing trials. And then we'll open up for questions, which can be on this or any of our previous webinars. So let's go right back to where we started at the beginning of this webinar series and ask why we need to control friction. So we need friction to be present in the wheel rail interface to be able to allow acceleration and braking to occur. However, we need to control that level of friction. Otherwise, it can lead to a number of issues and damage mechanisms to both the wheels and the rail. And we've discussed all of these issues in our webinar series and how friction management can help to mitigate against them. If you missed any of the webinars, they're all available on the LB Foster website to rewatch, and you can find the link to all of the recordings on the news page from the main LB Foster website homepage, which is www.lbfoster.com. So this table just summarizes the different issues that we've spoken about and which friction management regimes are particularly effective against them. You'll notice that some of them are listed as direct influences and some are listed as indirect influences. So just working briefly down the table, we have flange wear, gauge face wear. So obviously gauge face lubrication has a direct effect and a direct benefit against that. But friction modifier, friction at the top of the rail has an indirect. And that is because by applying a material to the top of the rail, we're reducing the coefficient of friction. Therefore, we're reducing the lateral forces and the angle of attack in the curves. So therefore, you're reducing the flange contact slightly. So therefore, it'll have an indirect effect on flange and gauge face wear. So you can read down the list for yourself. And likewise with flanging noise as well. Top of rail friction modification will have an indirect benefit in reducing flanging noise. And again, from our previous webinars, we've talked about the many different types of materials, friction modifiers and lubricants, and also the delivery mechanisms. So the trackside application of greases, or friction modifier or traction gels to increase adhesion, onboard application of solid sticks for flange wear or solid sticks for tread friction modification, and then onboard spray systems, so oil systems for flange wear and top of rail friction modifiers for tread wear and also noise corrugation, energy efficiency. So why do we need to trial friction management? Going back again to one of the slides from my first webinar, which was the introduction to FM, monitoring and measurement is one of the key aspects of an effective friction management program, alongside choosing the correct equipment, the correct consumables, and the correct maintenance and filling regime. So as operational and environmental conditions and the condition of equipment may change over time, it's critical to know that the equipment and the consumables are still working as designed and required. And so this monitoring and measurement will also inform any future changes to any of the other three aspects of the FM program, whether that's change to upgrading equipment or changing a consumable, or even changing the application rate of that consumable. Other reasons for undertaking trials and validation of friction management solutions. This list is not exhaustive, but typically when you're introducing a new product or a new equipment into a network, you will need some form of network approval from the either infrastructure manager or the rolling stock OEM or the network controller. So trials and validation are often required for this process. Your customer may want to quantify the cost benefits of a friction management regime prior to committing to a full-scale implementation. So you may want to do a limited trial. Obviously, you need to know if your friction management solution is effective. So a trial and a validation process is required for that. And also, is it optimized? Are you using the right application strategy? Are any trackside units sited in the correct locations to maximize the benefits? And also the final reason is, are there better options out there? Are there better materials, better equipment available to you to get a better result for your friction management? So what are we looking at in terms of the key aspects of an effective trial? So to be an effective trial, it needs to be objective. It needs to be as clear and as possible in terms of the plan and the results that you get from the trial. So you should always really start with a clear objective and success criteria. So it's good to understand what success looks like for the trial. What are the outcomes that you are looking for, and how will you determine whether this trial is successful or not? So there should always be a trial plan, which clearly sets out the scope and the details of the trial. So this should include details of the trial location, if it's a trackside trial, or the details of the specific rolling stock or vehicles, if it's an onboard technology, and also the route that those vehicles will take. If you're comparing two products, or if you're just comparing one product against baseline, the measurements should always be taken from the same location or of the same location, or curves if it's a trackside. So in order to keep the trial conditions as consistent as possible. So particularly in trackside trials, curves and track forces and vehicle rail interactions are never exactly the same for different curves, even if they have the same curvature. So you need to really normalize the location where you're taking the measurements from, so that you get as clear results as possible in order to make a good comparison between either baseline and product or different products. You need to define the timescale of the plan and take into consideration whether it needs to be a long-term test period, so taking in a number of seasonal environmental conditions, or if it's just a short-term test, for example, to take noise measurements, so comparing a baseline noise measurement against that using a friction management technique. The plan should also define whether you want supplementary laboratory testing and whether that's required before you even move on to the field trial stage. So that's I'll talk about laboratory testing in a little while. The trial plan should also include details of how you're going to measure, so what metrics or key performance indicators you're going to be looking for during the trial. Haven't got it on this list, but really you should also consider creating a risk assessment for the trial, considering not just the health and safety of the personnel that are going to be taking the trial, but also maybe addressing the technical risks of the trial as well. So what would happen if the trial does not go to plan for whatever reason? And laboratory testing can help to kind of back up and de-risk some of that aspects as well. The plan should also give details of the commitment and responsibilities of the different parties. So, for example, if LB Foster would be involved in a trial, we would lay out exactly what our activities would be, what our responsibilities would be, and what the expectations of the customer would be in terms of what they would supply. And then finally, the trial should give details of what the trial will deliver in terms of a report or presentations, or even calculations, so cost-benefit calculations. The correct methodology and equipment should be used for the trial. So, for example, noise measurements, it should be a fully calibrated noise meter. Or if it's a trackside system, then are you going to be using a tribometer, or are you going to be doing lateral force measurements? So choose the correct and appropriate measurement techniques and equipment. And then the baseline conditions should always be understood and established in order that you can make a clear comparison. All of these aspects are common sense items that you should include in an effective trial. So in some cases, you might want to undertake some laboratory scale testing as well as the field trials. And you may want to do these first before you even move on to a trial in the field. And so these are particularly useful when you're trying to understand the differences in the characteristics between different products from, say, different suppliers. There is a European standard for rail lubricating greases, EN 15427. And there are also technical specifications for top of rail materials and adhesion materials. And these all contain guidance on standard testing regimes and pass-fail criteria for greases, top of rail materials and adhesion materials as well. It should be noted that standard tests for lubricants for other industries that you might do might not necessarily be relevant to rail due to different contact conditions. So, for example, the standard 4-ball grease test is a standard test, but it's not really a valid or applicable to the sliding contact conditions in the wheel-rail interface. So you should use some caution in terms of what laboratory testing that you're using. Laboratory testing can correlate strongly with data from field testing, but not always because of the scaling aspect. So some laboratory testing may be required, but field testing is always the best in terms of getting the real world conditions. Some of the testing that can be done in the laboratory can be product durability or retentivity, pumpability, so how will the product, the consumable, work through the specific equipment. Climate chamber testing can be used to test the operating temperature range through the applicator bars, and also can be tested in the laboratory. Standard product tests such as water wash off and stability can be done for greases, both greases and top of rail materials. Safety data sheets are always a valuable source of information when comparing different products. And you may also find field data that's already published in the public domain, which can either assist in making a decision between products or can be used to assist in creating the trial conditions. So the images we've got here, we've got some lab testing, we've got a worked penetration test of grease on the top, and then we have a twin disc testing machine at the bottom. So just as an example, we've got here some twin disc testing of different types of greases. So the graph shows the coefficient of friction on the y-axis and time on the x-axis. Sometimes twin disc testing can be represented using the number of cycles, but either or is fine. So this graph shows the relative retentivities of different greases, different types of greases. So you have some petroleum greases, and you have a premium synthetic grease, and you can see the comparison between the different retentivities. So you could use this data in terms of refining the choice of products that you're going to trial in the field. So moving on to field trials. So when you're looking at field trials and designing a trial, it's particularly critical to reduce or isolate as many potential variables as possible in order to get as an objective result as possible. So items that you should consider when you're setting up a trial are obviously the test location. Is it an accessible location for measurement? Is it a suitable location? What are the traffic patterns over that location or length of track? What types of vehicles are running? Are they transit? Are they freight? Or is it a mixture of traffic? What's the frequency of traffic, or what the number of axle passes per day, or the tonnage passing over that site? What is the directionality of the track? Are there any unique local conditions that you need to take into consideration in terms of things like weather patterns, microclimate, particular geography? Is it in a deep cutting or an embankment? Those sort of conditions that may have an effect on the measurements that you're going to take. Track conditions are obviously key as well. So what is the track geometry? What's the curvature, the gradient, and also what maintenance regimes are already in operation on that particular railway or railroad? And will this actually influence how often you can get access to the track to take measurements or inspect the equipment? So moving more onto the specific types of trials, so measuring wear, so a wear trial. So rail profile measurements are typically taken when you're measured, obviously, to monitor the progress of the wear over time. And typically a handheld measurement device such as a Greenwood mini prof design device is used, which gives a highly accurate measurement of the rail profile. So we have one of the screen outputs from the mini prof device at the top right of the screen. So you can compare that with either a baseline rail profile or a standard new rail profile, and plot the wear rate over time and how that's progressing. So a mini prof can be used, or there are other optical devices such as a Calipari, which is an optical measurement device, which will do the same job effectively. Another option is, if it's available, is to use a rail geometry car vehicle. So in the US, there are a number of these vehicles which are used by different railroads, and these give an automatic measurement of the rail profile and also log the location and time. So you can use the data from these geometry cars to actually give you your rail wear over time so that you can monitor it. So here's an example that was taken of a specific railroad at the milepost MP 3.6 miles. Southbound traffic, it's a right-hand curve, and it's 295 meters radius. And these measurements were taken from the high rail. So we have here across the x-axis, you've got million gross tons. So in 100 million gross tons increments. And then you have the rail wear in inches measured on the y-axis. And then you've got time stamps across, giving you the wear against time. So you've got, so on the left, you have the baseline wear and how that is progressing over time. So the gradient basically gives you the rate of wear of the rail. So the first red vertical line gives you a timestamp when the curve was re-railed, and then the monitoring of the rail started again. So periodic rail wear measurements were taken over a period of about 3 years. Again, you can see the trend. So you see that the rate of rail wear, which is fairly similar to the first one. And then the rail was renewed again. So the second red line shows the rail renewal. And then the green vertical line shows you where the friction management was optimized. So the friction management regime was implemented, and then you can see the trend in the rail wear. So obviously you can see that the rail wear rate is greatly reduced. And so this is effectively a very successful trial in this particular curve. So taking friction measurements is also a useful trial in terms of validating the friction management regime, but also establishing a baseline of the original friction measurements for that particular location. So a number of techniques can be used. Push tribometer is probably the most common. So this is a portable device that can be pushed along the track that will give you a friction management either on the gauge face, the gauge corner, or the top of rail. So friction levels can be used to measure the carry down of greases. It's not so effective on measuring the carry down for top of rail materials in some conditions and depending on the products. So again, it's going back to using the appropriate measurement technology. And here you can see an example of a location. So several miles of track with tribometer friction measurements taken on gauge corner, gauge face, and also top of rail. Another measurement technique is taking lateral and vertical force measurements, so L/V measurements, as we term them. And these tend to be more effective for measuring carry down and effectiveness of top of rail materials, mainly because it's quite difficult to, with a tribometer, to measure the carry down. Some products, particularly freight products, it's more difficult to actually detect them in the contact patch as you're moving down the track. And so L/V measurements are much more reliable. So to do this, strain gauges are attached to the rail. So you can see in the picture, you can just see on the web of the rail, the strain gauges have been attached to the wheel, and then obviously signals are sent back to a data logger, which in this case is solar powered, and then you can extract the data from that. So you can measure over a long period the lateral and vertical forces on the rail. So these measure both lateral and vertical forces, and these can be then used to compare different friction management materials. So the data that you achieve can be displayed in a number of ways, either as a scatter plot, so on the left, or as a histogram or a distribution. So you can clearly see changes in lateral forces by applying friction management, or as well, in this case, you can actually see the difference in lateral forces when the rail has been ground, which is the first purple tag, and then when the rail's been tamped as well. So it's not just for friction management. L/V can be used for a number of different trials. Visual inspection is also used, can be used for measuring the carry down and coverage of gauge face grease materials, not so much for top of rail materials. It's an easy technique, but really it needs to be done by somebody who's experienced in assessing the visual effects of grease on the rail. So you can take photographs and you can see over time that the grease is being carried down. So you can put, as is shown here, put tape on the rail at different distances, and you can actually see by removing the tape whether the grease is actually carrying down the track. Noise trials are a specific type of trials, so you can measure baseline against a noise level with or without friction management. You should always undertake to take background noise measurements, so you can compare the product against the baseline. So measurements, there is a standard for measuring, taking noise measurements, and this is BSEN ISO 3095. So this dictates that you should take noise measurements ideally from 7.5 meters away from the center of the track at a height of 1.2 meters. So this is a standardized position of measurements. So the position where you take the measurement from also is dictated. So you should always take the measurement in the curve where the angle of attack is fully developed. So as close to the center of curve as you can possibly. Weather conditions can affect noise measurements significantly. So dry weather conditions are required. Any moisture or rain will affect the friction levels and therefore the noise levels. And the maximum wind speed of 5 meters per second should be applied for any noise measurements. So you record the peak sound and also the frequency distribution. So you can see a couple of graphs at the bottom where you have the baseline measurements, which is the red, and then the blue with the friction management. So you can see the change in the noise or the sound pressure levels, but you can also analyze the difference in the frequency distributions. And I talked quite a bit about this in our noise webinar. Corrugation trials is another one. So again, you should choose a site where obviously corrugation is an existing issue and use correctly calibrated and appropriate equipment. In this case, a corrugation analysis trolley or a CAT trolley. Again, establish the baseline measurements. So this is a little bit more involved. So in order to get a good trial, you need to start off with a clean rail. So either start off when the rail has been freshly ground or replace the rail or has been replaced to ensure that there is no corrugation. So then obviously leave a certain period of time to allow the corrugation to grow, and then take periodic measurements over time to measure the growth rate. And you should ensure sufficient time is left to give you enough time to get a significant corrugation growth. And then you should repeat the grinding to ensure that the corrugation is removed again, implement the friction management, and then take, again, periodic measurements to measure the corrugation growth. And hopefully over the same time period or the same gross tonnage passed as the baseline growth measurements. And that gives you an easy comparison. So then you can compare the growth rates and assess whether the friction management has been effective and how effective it is. Typical length of a trial for corrugation tends to be a bit longer, so it tends to be 8 months to a year. If you have extreme corrugation growth, very rapid corrugation growth, then you could probably do that quicker. Measuring the equipment performance is also an important validation technique. So you need to know that the application equipment is working as intended in terms of how much product is being pumped, and so that the output is as you expect. So remote performance monitoring functionality can be used to measure this. You can see a graph at the top in terms of product level in the tank. So you can look at how much product is being used over time. Is that as expected? You can also use remote performance monitoring to monitor the unit uptime. Is the equipment reliable? Bar clogging, particularly for trackside units, obviously is critical in terms of, are the bars distributing the same amount of product every time over time? So port clogging on applicator bars is critical to be monitored. And this obviously heavily affects the maintenance. So different greases may have different performances through bars. So some of this you can do in the laboratory, but obviously this is not a real life condition out on track, taking into consideration environment and equipment as well. So you need to really do trials. So you can see here at the bottom, you've got the same bars. So you have a petroleum-based grease, and you can see that there are only limited ports that are clogged. So this is after a period of time that the bar and the product's been in use, so that some of the ports are clogging. And then compare that to a different product. So this is on the right is a synthetic grease over the same time period, and you've got many more ports that are distributing the grease. So it's a much more effective grease, much less clogging. Site cleanliness as well is also important. If the bar is not effectively distributing the grease and transferring that to the wheel flange, it's going to be wasted. It's going to end up in the track. And so this is obviously an environmental concern. So site cleanliness is another area that you may want to monitor. The grease itself, also the performance is important in terms of grease separation. The grease is sat in a product tank. It could be over a long period of time, and most greases, most gauge face units will show some oil separation over time, but the amount is critical to the performance. So if you have a high amount of grease separation, this will affect your bar performance and will accelerate or exacerbate bar clogging. So it's important to monitor this. So you can see there's a picture here with a red circle. You can see that there's a high level of grease separation of the oil in that tank. The stability of the material as well is important. So the consistency and how stable it is over time. How well does it perform in terms of through the bars, in the product tank, in terms of it moving down the tank? Does it slump fully into the bottom of the tank? Does it cavitate? Does it stick to the walls of the tank? Is there a uniform product draw through that reservoir? And also, finally, temperature is the atmospheric, the environmental temperature. That will have an effect on certain greases that are either could be a summer grease operating in winter, or a winter grease operating in summer, or an all-season grease. So temperature has a large impact on the performance. So you need to look at output rates, carry down, and wheel pickup, which might be affected. Also, top of rail materials you need to monitor, particularly consistency and stability over time in the tank. So you can see on the right an extreme where the product has degraded and has separated, and obviously this is going to have a big effect, not just on the bars, but also on the operation of the pump. So you may find that your pump is starting to fail or seize because of poor product stability. Output rates you should monitor in terms of, are you putting out the amount of material that you think you are? And this may degrade over time as the pump age in service, or as the temperature range changes, or comparing product versus product, or unit versus unit. So it's good to periodically test the output rates of the trackside units, as this output rate can also influence the effectiveness of the friction management regime, but also the economics as well. If you're actually using more product than you think you are, or not as much as you think you are, this will have an effect as well. So this can either be tested in the field, so going out and testing the equipment, removing the material from the bar and weighing that to test that against what the calibrated output should be. Or you could use a train simulator. So a train simulator, such as the one shown on the right, can be used to actually simulate this in either in the laboratory or in the field. So this is hooked up to the wheel sensor and simulates traffic patterns. So you can dictate wheel pass frequency or length of train, frequency of train, and also the speed of the trains as well, and test the output against what the calibrated output should be. And so this can be done for both gauge face greases and topper rail materials as well. Final onboard equipment trials, so solid stick trials, a couple of different trials. The first is wheel wear. So you can trial the solid stick systems and plot the wheel wear over time against the baseline wear that you have without the friction management. So establish the baseline wear rates and compare that with the standard wheel profile. So again, a mini prof or a calipari can be used to measure the wheel profiles and compared against the standard wheel profile of the new wheel. So you can see here, top right, you have a profile. So the red is the baseline wheel profile, so a new wheel, and then the blue is a worn wheel. Or you can monitor the tread hollowing. So again, you've got the standard tread profile against a worn tread profile. So you need to choose a control train, which doesn't have the friction management, and a test train. So you may want to do 2 or 3 control trains and test trains. Monitor the mileage for each. Monitor also the wheel turning on both vehicles. Obviously, if you turn a wheel during the trial, then that kind of skews the results. So you need to eliminate any turned wheels from your analysis. It's also key to measure the wheel profile in the same position on each wheel every time. So it's good to put some sort of mark on the wheels so you know where to measure each time that you do a periodic wheel measurement. So you can see on the picture bottom left, there's an index mark on the wheel where you would take the mini prof measurements and take several measurements through that trial period and monitor the change in wheel profile. Another is a solid stick trial, so looking at stick consumption. So this is looking at more for the economics and the effectiveness of the sticks in terms of working out what your cost benefit analysis is going to be. How many sticks a year are you going to be using? Or you may want to compare one type of stick against another from a different manufacturer or from the same manufacturer. So a number of aspects that you need to consider for stick consumption trials. One thing to do is never to mix stick types on the same vehicle. Because solid sticks act and they transfer to different wheels, the sticks will interfere with each other. So if you have, for example, on the front of the train, one type of stick which has a higher retentivity and is more effective than the other, then the ones that follow it will be affected by this and they'll have a lower consumption rate. So that will skew the results. So keep different sticks on different material and different vehicles to keep the results clean. So before you start the trial, you should ensure that the applicators are all in good working order. Ideally, you should change the constant force springs so that you're starting off from effectively a new applicator. The springs do fatigue over time, so you do get a slight degradation in the spring pressure. So it's good to start with new springs throughout the trial. And also check the alignment of the applicators to make sure that they're fully aligned. So to do the trial, you should weigh each of the sticks before use and clearly identify the types of sticks and where the sticks are in the applicators, and also identify the applicators. So the top right picture shows an applicator in a trial. So you can see that it's been marked number 2, right-hand side. So clearly identify and uniquely identify each applicator that you're using during the trial, and also the sticks. And then the test vehicles should follow the same route with the equivalent mileage. So you should record this as well over the time period of the trial. And that time period is really up to the user in terms of what their usual consumption and maintenance refilling intervals are. So record any stick refills during that interval and weigh the sticks after use. So from that, you can calculate the consumption rate. And here we have a table just showing an example. So showing LB Foster stick versus another product. So you have the average consumption in grams over the time period, the average consumption rate over the time period. And then because you've located the mileage, you can actually calculate the consumption rate in grams per 1,000 kilometers in order to give you a clear comparison between the two products. So just to round off, there are a number of resources that you can draw on for looking at testing and trialing in terms of good practice and also standard procedures. So the EN 15427 series of standard is there, it's published. The gauge face greases, parts 1.1 and 1.2 are standards, and the remaining parts are technical specifications, which will become official European standards in the near future. So all of these contain standard tests for gauge face materials, adhesion materials, and top rail materials. But also there are a number of appendices looking at different trials that you can use. Particularly the adhesion, there is a standard braking trial procedure that you can use if you want to do some braking trials. Another useful resource is the Rail Safety and Standard Board, RSSB's Spark resource website. So this is an online resource and reference library. There are thousands and thousands of research documents on this website that's fully searchable. It's free to access. You just need to register and get a log on. So there are research papers going back several decades in terms of rail research, testing, academic research. So it's fully searchable. And all of the documents or the majority of the documents are free to download as well. So it's a really, really useful library to look at previous field trial data that's available. And obviously you can do a Google web search as well to look in the literature. So finally, in summary, we've just done a brief recap of the issues and what we've talked about in the previous 7 webinars. Why do we need to undergo the trials and validation? And then we've gone through the trials best practice, what defines a successful trial, and the different types of trial that we've looked at. Useful resources. And that's it. Thank you very much. Just as a reminder, all of the recordings are available. So I'd like to open up for questions. If you have any questions on trials or any of the previous webinars, I would be happy to answer them. Thank you for that thumbs up. We're going to be sending out a quick questionnaire just to get your feedback on the webinar series. If there's anything that we've missed that you really want to know about, and if if this has been of any use to you whatsoever. We'd really love to have some feedback from you. So if there's no questions, doesn't look like anybody wants to ask any questions. You've got my email details on the invite emails if you want to contact me, or if you want to speak to anybody else from LB Foster, please let me know and I will be happy to put you in touch with people. Thank you very much.